We know there exists this interesting analogy between translation and rotational motion. It doesn't mean the translational quantity and rotational quantities are equal to each other, okay? They just correspond to each other. But when an object rotates, you look at a point, this blue dot on that object. We can look at the motion of this object two ways. We can study its rotation. We can also study the translational motion of that blue dot. And we find that the rotation and translational motion are related to each other. In other words, it's obvious that if the angle covered doubles, then the amount of arc length that goes through also doubles, right? There are some relationships between the translation and rotational part. So we're not just looking at analogy here, we're looking at exact equality that relates the translation and rotational motion. Okay, this object went from here to there. The distance between the object and the center of rotation, axis of rotation, is r. And r does not change because that's a rigid object, right? It cannot deform. Okay, so that blue dot moves a circle, part of a circle, and the arc length is delta s. What is the linear speed of this object? Average linear speed. That will be distance over time. Distance is the arc length covered, and that is delta s. Okay, that is delta s. So delta s over delta t. That is the linear speed v. But exactly what is delta s? Well, that's part of the arc length, that's length of an arc, and that of course is delta theta times r, right? Delta theta times r. So I can rewrite this as r delta theta, and then divided by delta t. Now, what is delta theta over delta t? Isn't that equal to omega? So that's r times omega. This is a formula that actually equates the linear movement with angular movement, and it turns out v and omega are proportional to each other, and the constant proportionality is r. So let me rewrite this formula here. It will be widely used. V equals omega times r. So different points on the rigid object will have different values of linear speed, even though they have the same omega. If it's rigid, it's got to have the same omega if it's a rotation about fixed axis. Omega is the same, but if the distance between that point and the axis of rotation is different, then v can be different. A point right on the axis of rotation will not move at all because r is equal to 0. And an object further away, like say there, from the axis of rotation will have to move faster to keep the same angular speed. Okay, now this is the relationship between linear speed and angular speed. In fact, sometimes we use a letter t to denote that this is translational motion. Okay, it's translational, not radial movement. In fact, there is no radial movement at all. Next, let's look at the acceleration. Linear versus angular acceleration. How are they related? Again, I have this object, this blue dot, that's part of a rigid body. Okay, it's doing this motion like this. It's doing a circular motion. Anything that's doing a circular motion must be subject to a centripetal acceleration that turns you around. That's a r. R means it's radial. Okay, it's along this distance r. But it's also centripetal. It points toward the center of movement. And on top of that, this thing can also speed up or slow down, which means there can also be a tangential acceleration. Okay, so that's a tangential. Here's a radial. Now, if you add them together, you get the net acceleration a of the object. In this particular case, the net acceleration, the angle between a and v is here, which is less than 90 degrees, which means a tangential is parallel to v, which means it's going to go faster. Okay, so it is an accelerated, non-uniform circular motion in this particular case. The question is, how do we calculate AR and AT? Well, AR is simple. The magnitude is simply v squared over r. We know that. R is the distance between the point and the axis of rotation. But what I want to do now is I want to rewrite v in terms of omega. We know how to do that. We just got that. That is omega r. Square it and divide by r. So that equals omega squared times r. So you see, even though in a rigid body rotation, every point has the same omega, they do not have the same radial acceleration or centripetal acceleration an object that's at a point that is further away from the axis of rotation will have to experience a greater centripetal acceleration because it's proportional to r, the distance between that point and the axis of rotation. Okay, and what about tangential? You see, if you move faster in this direction, okay, then you'll have a positive tangential acceleration, right? Because you go faster. But that also means that you're going to turn around faster, which means alpha is also positive. How is AT related to alpha? Well, you know, Vt, right? Vt equals omega times r. Vt is just that V, the same thing, except I want to emphasize this is tangential movement. If I take a derivative with respect to time for both sides, okay, I'm not taking derivative with respect to the whole v, to the whole velocity, because if I did that, I would have obtained that acceleration as well. Just the magnitude of the velocity, just the speed. Okay, so what is dv dt? Just the speed, no vector sign. Well, let me take derivative with respect to the other side as well. R is a constant. Why? Because it's a rigid body. The distance between that point and the axis of rotation cannot change. So R is a constant, but I do have d omega dt. What is d omega dt? Isn't that alpha? Right? Isn't that alpha? So that's R times alpha. What is dv dt? dv dt is the rate at which the speed changes. That is, by definition, tangential acceleration. See? Okay, so I have an expression for both radial and tangential acceleration. They're related to omega and alpha. So let me write them down again. Again, these expressions will become very useful. Radial acceleration or centripetal acceleration equals omega squared times r. Tangential acceleration is proportional to alpha, so it's alpha times r. If an object rotates with a constant angular speed, then alpha is equal to 0, at is also equal to 0, because every point is doing uniform circular motion. Of course, there is no tangential acceleration. But at any point, whether it's uniform circular motion or not, you must have radial acceleration because you're doing a circular motion after all. So as long as omega is not equal to 0, you always have radial acceleration. With the analogy between linear and translational motion, we were able to finish the discussion about rotational dynamics. Rotational kinematics, that's what I mean. Really simple. Now let's focus our attention on the dynamics of rotation. You know, in the dynamics of translation motion, we introduced first force and mass, right? Then we introduced other things such as momentum, impulse, that sort of thing. And energy, of course, kinetic energy and potential energy. We're now going to do a parallel discussion for the dynamics of rotation. We're going to start from something we already know. That is, how does one calculate the kinetic energy of an object in rotation? Well, the thing about the object in rotation, again, every point would have different speed, different linear speed, even though they have the same angular speed. So what we need to do then is to look at a rigid object point by point. We can break it down to many, many small points. Each point, let me find its linear speed from its angular speed. Let's find its linear speed, and from its linear speed, let's find its kinetic energy. Then we're going to add the contribution from all these points up. Okay, so let's look at this point, point P. It is located at distance r sub I from the axis of rotation. Okay, so how do you draw this red vector? You just start from this point in question, right? You drop a perpendicular to the axis like this. Okay, you find a distance r sub I. Now, this point P, just like any other point, is doing a circular motion. Okay, it is doing a circular motion about this axis, So what is its linear speed? What is v sub I? Well, we know that v sub I equals omega times r sub I. We learned that before. You notice I didn't put a subscript I on omega. Why? Because omega is the same for every point. So as this I changes, 1, 2, 3, 4, whatever, omega stays the same. That is the nice thing about rigid body rotating about fixed axis. Okay, let's say the mass of this point is m sub I. So what is the kinetic energy then? Well, the kinetic energy, K sub I, would be equal to 1/2 m sub I vi squared, right? Okay, let's work it out. Isn't that equal to 1/2 mi Vi is omega times r, so I'm gonna square it. Isn't that equal to omega squared Ri squared? Okay, this is just the kinetic energy of this little point. What is the kinetic energy of the whole piece? I need to sum over I to add up the contribution from all these points, right? So the kinetic energy of rotation, R for rotation, kinetic energy of rotation is the sum over all the K's for individual points. Let's do the summation, shall we? Let's do the summation. You do the summation, 1/2 mi Ri squared omega squared. Okay, these two quantities, mass and radius squared, both depend on I. It varies from point to point, but omega is the same for every point, so is 1/2. So what I'm going to do now is I'm going to take that constant 1/2 omega squared out. Okay, so here's what I get. I get 1/2 and I get omega squared. I'm going to take these guys out. But what's left though is this combination in the middle, the sum over the entire object, mi Ri squared, right? This thing here. This is a combination which of course you can calculate based on the shape and size and mass of the object. Let me call this, give it a name, we call it I. This letter I to denote it. Then I have an expression for the rotational kinetic energy of the object, and I find that the kinetic energy of rotation, Kr, equals 1/2 I omega squared. This I'm still going to use a red color for it because it's a new quantity. We're going to focus our attention on I in the next step. You know, we wanted to focus on the analogy between translation and rotational motion. In translational motion, we know how to calculate the kinetic energy, don't we? It's 1/2 mv squared, right? Okay, I still have a 1/2 here, but look at the analogy here. V, the linear speed, of course, is replaced by angular speed. The reason I want to use angular speed over linear speed is because, after all, for a rigid body, omega is the same for every point, but V is not. That's why I use omega. Okay, so you see, if you look at the analogy again, this corresponds to V squared. 1/2 is always just 1/2, still 1/2. Kr is now K translational. But what about this I here? What does I correspond to? Well, in one-dimensional translational or even three-dimensional translational motion, you know the translational kinetic energy is always equal to 1/2 mv squared, right? So m. You see, what did that tell us? It tells us that this I resembles or it corresponds to the mass for linear motion. So I have this strange quantity, this strange combination. It depends on the mass, but it's not equal to the mass. It depends on the mass. It also has to do with where these masses are. Okay? After all, r sub I is the distance between the ith point mass and the axis of rotation. So it has to do with the mass. It also has to do with the distribution of mass. This quantity, I, replaces the simple quantity m for translational motion. This I, we have a name for it. You know, in translational motion, we know mass is the quantity of inertia, right? It's the quantity of inertia. Here I have rotational motion. Therefore, this I is the quantity of rotational inertia. And we just sometimes simply call it rotational inertia. Sometimes called moment of inertia. The reason why we call it moment of inertia, that's a mathematical term because, you know, in mathematics, you know, you go mr squared, that's called the second moment because there's a squared here. It's just a mathematical term. But it's also called rotational inertia. So you see, this thing should take the same position as mass. Mass tells you the ability to resist linear acceleration. So if you believe the analogy, then this I here should represent the ability of an object to resist angular acceleration. We'll get to that later. But for now, let us see how we can calculate rotational inertia. It's not something that might be so straightforward at all times, because after all we have to do this summation. I equals to okay, this is the formula we use, right? Okay, first thing first. Even though the mass of the object is fixed, even though the shape and size can also be fixed, this quantity is still undetermined unless you tell me where is the axis of rotation. Because after all, r sub I, again, is the distance between the ith point in the object and the axis of rotation. And if I switch to a new axis, of course, all these r's are going to change. Okay, so you get a new quantity I. So you see, it makes a difference which axis you use as a rotational axis. You will get different values of I, and since I represents, the ability to resist angular acceleration, when you rotate this object about different axes, you may get different degree of easiness. Sometimes you find it's rather easier to accelerate it because I is relatively small for that particular axis. And so let's see how we can calculate I. Okay, we're going to look at two different cases. One is a case where the object is made a whole bunch of discrete point masses. The other is a more common case when the thing is made of a continuous distribution of mass. So, here is our first case. Let's calculate I. Discrete particles. Okay, the object is made of a whole bunch of point masses. 1, 2, 3, 4. I can count them. They're discrete. Let's look at this very simple case. We got only 2 point masses, m1 and m2, separated by distance L. Let us calculate the rotational inertia or moment of inertia of this dumbbell-shaped object. Again, I have to choose an axis. Without the axis, I don't know what I is. For example, let me choose an axis perpendicular to the line connecting these two. And it also passes through one of the objects, one of the masses, m1. So here is my first axis like this. Okay, so suppose I rotate this object about this axis. Let's call it axis 1. What is rotational inertia? Okay, let's see now. I have to do the summation, right? I have to do the summation. I equals sum of mi/ri squared. In our case, the sum has 2 terms because there are only 2 objects, 2 point masses. m1 r1 squared plus m2 r2 squared. Okay. What is m1 right here? What is m2 right there? What about r1? By definition, it is the distance between the point mass m1 and the axis. And that is 0, of course, so that's 0. The next one, m2 r2 squared. What's r2? The distance between the second point mass and the axis of rotation, which is L. So we get m2 L squared. Very simple. Okay, so that is how we calculate rotational inertia about a certain axis for an object consisting of discrete set of particles. Of course, if I switch to a new axis, here, I'm going to get different results. Or if I consider a case when m1 and m2 are equal, look at the symmetry, and then I go to the middle. Okay, I'm going to place it in the middle. So here's axis number 2 here in the middle. Well, the masses don't have to be equal. Let's first consider them to be different. So this is I1. How do I calculate I2? I2 would be again m1 r1 squared plus m2 r2 squared. But here r1 is the distance between the axis and m1. That is half of L, right? So it's m1 half of L squared. And then you have m2 half of L squared. Right? So I can write this up. This is just m1 plus m2 times L squared over 4. It is L squared over 4. It is very different, really. It is very different from this case, which is m2 L squared. So I1 and I2 are different because I use different axes. In particular, if m1 and m2 are equal, let's call it m, just simply call it m, then this becomes, okay, this is 2m, right? So this will be L squared, ml squared, over 2. And here, if m1 and m2 are equal, this will become ml squared. You see here, ml squared and ml squared over 2. Obviously, I1 is twice as much as I2. Why is that? Well, in general, when you look at an axis pretty far from the center, okay, pretty far from the center, like about one edge, then as the thing turns around, this guy is pretty far, right? Pretty far from the axis. And therefore, as it turns around for the same angular speed, it's got a large arm, which means its linear speed is large, which means you get greater rotational inertia. Okay? On the other hand, if you put it in the middle, then these particles are closer, on average, closer to the axis of rotation. So even though they have the same omega, they do not have the same amount of kinetic energy because the linear speed is relatively small. So that is why, qualitatively, I1 is greater than I2. But we're going to look at more details, how to get I1 and I2. In particular, you see these two axes are parallel to each other. We're going to learn a theorem later, which tells you that if I have two axes parallel to each other, and if I know the value of I about one axis, and I know the distance between the two, I also know where the center of mass is, I can immediately tell you what is the value of I2. Okay, before we do that, let us look at the case of a continuous distribution of mass. Continuous